Hello, everybody. So today we're going to talk about space complexity in this video, and this will be a much shorter discussion than the discussion we had for time complexity, just because we don't have any more time in the class. In fact, this is going to be the last video in the main stream of this class, but we're going to see several advanced topics that I think are as exciting as anything else that is in the class in the next videos. Some of them are going to be very exciting, and you can continue all of them in other courses in Stanford. Specifically, the most natural one is in 254, but I'll discuss more of this on Piazza. So space complexity, you can see that there is lots of complexities of being in space. And let's mimic what we did for time. Let's kind of ask how do you measure space complexity? We have a finite state control, and we have our tape. The tape has the input in it, and we also read and write on it. And you can look at every cell that you reach and number it, the first one, the second, the third, and you can essentially measure the space complexity by the index of the largest index of a cell you can reach. So we measure space complexity by looking at the largest tape index reached during the computation. Some computations, you'll go a lot to the right and you'll touch more cells. Other computations, you'll just stay close to home, and then it means that you're using less memory. Let's M be a deterministic Turing machine. The space complexity of M is a function, S, on the natural numbers, where S of n is the largest tape index reached by M on any input of length n. So for a single machine M, we're talking about, and for a particular input length n, we're talking about the worst input, the input that makes you use the most space. This is your space complexity. Again, here we can talk about other things like rather than worst case, but to keep this class simpler, we're just talking about worst case complexity. Space S of n are all the languages that are decided by some Turing machine with order S of n space. So this is the minimum over all the Turing machines that decide L of their space complexity. So the minimum over Turing machine of the maximum over their inputs. Let's give an example. We look at 3SAT, which is a complicated problem, but in fact, in terms of space, it can be using linear space. By the way, we won't talk about less than linear space, although it is very interesting. There are lots to say about less than linear space, but then we need to be much more careful about defining space. The way we define space so far would only make sense if we're thinking about things that are more than linear. So 3SAT, which is a complicated problem in terms of time, sits in space n. The reason is that you can try all assignments, all possible assignments to a formula, and there are at most n variables if n is the length of the formula. And this can be done in order n space, this enumeration, and then once you have a particular assignment, checking that it satisfies the formula can still be also done in linear space. It's not hard. Another interesting statement that's somewhat related is that non-deterministic time T of n can be done in space T of n. And the reason is that the witness, if you have a non-deterministic time T of n machine, its witness is going to be of length at most t of n, and you can enumerate all the witnesses and check if one of them is accepting. Put a little bit differently, you try all possible computation paths of order t of n steps, and for that you need to enumerate all the decisions you need to take in every step, and enumerating all of those can be done in order t of n space, because at every given point you can make one of several choices, but these are a constant number of choices that depends on the machine. The class space S of n formalizes the class of problems solvable by computations with bounded memory that's bounded by S of n. And a fundamental question that we don't have a complete answer to is what's the trade-off between time and space? So for example, how much time do you need to decide space n computations? For example, space n squared problems could potentially take much more than n squared steps to solve. When we talked about 3SAT, we did it in linear space, but the time that we used was exponential because we enumerated all possible assignments. And we don't know if there is a linear time algorithm for SAT. We probably don't believe that. And the intuition why you can have such small space compared to the time is that you can reuse space, but you cannot reuse time. So you write something on the tape, like a satisfying assignment, and then you check something, you don't like it, you write the next satisfying assignment on the same location. You don't need to remember it. On the other hand, time that you already used, you cannot reuse. You can say, okay, I didn't like what I did so far, erase the time I used for it, and let's try again. So time complexity of space S of n is not necessarily time S of n, but let's ask how many, what's an upper bound? How much time in the worst case can you do if you have a machine that uses S space on a particular computation? The number of time steps is at most the number of possible configurations that you can have with this amount of space. So if you have a machine M that on input X uses S bits of space or S symbols of space, then the number of configuration it can be in is exponential in the space S. If you remember, the configurations is the content of the tape, the location of the head, and the state. The major thing is the content of the tape, which is exponential in the space you used. And the time for running is at most the number of configurations, because the moment you are repeating a configuration, it means you're going to loop forever. And again, the configuration of M is specified by the head position, the state, and S cells of tape content. And the total number of configurations is at most S, which is the number of locations for the head, times Q, which is the number of states, times gamma to S, which is exponential in S. So the time, if you run in space S of n, you run in time at most 2 to the order S, unless you loop. So when we really want to talk about computation that always halt. So space S of n computations can be decided by 2 to the order S n time. So space S of n is contained by time 2 to the c to the s, 2 to the c times s of n for all all c. So you can buy in this exponential more power by using a Turing machine that has a larger alphabet tape, but this only gains you a constant. After 2 to the order Sn time steps, an Sn space-bounded computation must have repeated the configuration, so it will never halt. And space Sn computations are those that actually halt. Let's define the class P space, which is the union over k in n of space n to the k computations. Just like we defined polynomial time, this is polynomial space. And exponential time is the union over k in n of time 2 to the n to the k. So all exponential functions. P space is contained by exponential time just by the argument we had before. If for some k you have a space n to the k computation, it is contained in times 2 to the order n to the k computation, and therefore you get that P space in general is contained in exponential time. What about P and P space? Is P contained in P space? The answer is yes. Why? So we said it a few times, the space is bounded by the time. Every step you can reach a new cell. If you run in time t, your space is at most t. Therefore, every polynomial time computation uses already polynomial amount of space. Is NP contained in P space? The answer is yes. In fact, we already said that n time t of n is contained in space t of n, just because you can enumerate all the non-deterministic choices in the same space. Is NP to the NP contained in P space? Yes, because you can simulate the NP oracle in P space, and then you can simulate the algorithm that uses it also in P space. And so the space just grows linearly. So you need a space for the machine and the space for the oracle. And you can do it a constant number of times. So NP to the NP to the NP to the NP will still be in P space. In fact, you can do it polynomial number of times. So what you have here is P is contained in NP, contained in P space, contained in exponential time. And here are the endpoints the same here? Well, they're not, because P is different than exponential time. Why is it true? It's true because of the hierarchy theorem. Every more time buys you more power. You don't need to grow so much, but definitely time which is exponential in n is not contained in P. It buys you much more power than P. So therefore, P is different than exponential time, but we actually don't know. So this means that somewhere along the path, there is a strict containment. Either P is different than NP, or NP is different than P space, or P space is different than exponential time. But we don't know how to prove any of those. So although the endpoints are dramatically different, we don't know where along this very short path you don't have containment. So lots of things that are open. Let me mention the space hierarchy theorem, which is actually more tight than the time hierarchy theorem. We won't discuss the proof. The intuition is that if you have more space to work with, you can solve strictly more problems. So for every s, small s and big S, where small s is little of big S, meaning that small s over big S goes to 0 as n goes to infinity. space S of n is strictly contained in space big S of n. There are problems that you can solve in big Sn space, and you cannot with small Sn space, which is tighter than we had for the time complexity. The proof is just as before by diagonalization. I'll just give you a hint, but you don't need to actually know how to reconstruct it. So we will enumerate all machines that uses a small Sn space. So it's kind of enumeration, just like we had an enumeration with the clock, we can have an enumeration with a bound on the space. The moment you go beyond it, we just cut you off. And then once we look at this sequence of machines that use the smallest n time space, we can look at the diagonal and reverse it. This will be another language that can be decided in big Sn time, but it does the opposite of any of these machines, at least in one location. This was too complicated, then ignore it. This is just the diagonalization argument that we're doing often. The language that we'll get will be in space big S, but not in space little s, because it will be the opposite of the diagonal of all little s of n space machines. Let me discuss a little bit about non-determinism. It's still very interesting, the relation of non-determinism in terms of space, but it is a little bit less dramatic than it is for time, and we will not discuss it in more detail. So let n be a non-deterministic Turing machine that halt on all inputs in all of its possible branches. And the space complexity of this non-deterministic machine is a function such that none of this computation path uses more than f of n space on input of length n. So just like we talked about non-deterministic time complexity, we wanted the time that is used to be bounded for all computational paths. Here we want the space to be bounded for all computational paths. So non-deterministic space S of n are all the languages that are decided by some non-deterministic Turing machine that has order of S of n space complexity. Savage's theorem, which I will not prove, it's actually pretty easy. I don't know if they still prove it in algorithm classes, and I'll be happy to discuss in our meetings. Shows that for every nice function S, nice is again constructible in some sense, which is larger than linear. So S of n is larger than n for all n. Non-deterministic space S of n is contained in space of S of n squared. So you only pay quadratically in space for non-determinism. In time, you may pay exponentially. In space, you only pay quadratically. Quadratic blow-up in space is still pretty significant, but it is not as dramatic as exponential time. Open is whether non-deterministic space S of n equals space S of n. So could you de-randomize without any cost in space, or at most a constant? Very interesting problem. Not a lot of progress on it for the many decades since Savage's theorem. Non-deterministic non-deterministic polynomial space is the union for every k of non-deterministic space n to the k. And what we have here as a corollary of Savage theorem is that non-deterministic P space equals P space, because for every specific K, non-deterministic space n to the K is contained in space n to the 2K, which is still in P space. So let's see what we learned so far. We have P, NP, co-NP, and their complete problems. We have P to the NP, we have NP to the NP, co-NP to the NP. All of those are contained in P space. In fact, even if you continue to do NP to the NP some polynomial number of times, it will still be in P space, and in some sense it will capture P space. And beyond that, we have exponential time, and all of this is still just a small point in the world of decidable languages. We can talk about doubly exponential and triply exponential time and so on. But that would be enough for us. So some parting thoughts about what we had here. More space is more power. And the relation between time and space is wide open. We don't know it. Polynomial time hierarchy is contained in P space. So all these P to the NP are contained. And they contained interesting problems. In particular, P space does have complete problems. One of them is chess and other kind of games. Of course, chess by itself is of a constant size, a large constant size. So chess by itself can be determined in constant time. But if you think about a generalization of chess or other interesting games, these will be P-space complete. And they are not in the polynomial time hierarchy. So they are in beyond, so they're very, very interesting, but they are beyond this NP to the NP, etc. I mean, this is our assumption that they are beyond. Non-determinism may reduce space, but not as dramatically as time. So this was a very condensed discussion of space complexity, condensed in the sense that we went through lots of results and lots of relations. But I hope that you enjoyed these connections that are really non-trivial. Thank you.